Hi, this is Group 108, and this is a presentation on the topic image classification on the Tiny ImageNet dataset. So, for a problem statement, so ImageNet is a very classic benchmark. It is used for training different models like CNNs, different image detection models. And we wanted to kind of play around with it. We wanted to figure out different architectures, different models that we could do to make a very good image detector. ImageNet itself would have been too big for us. It has around 1,000 classes with a bunch of different images, and building a model to accurately get most of those would have been tricky for us in our time. So we decided to take a subset of that called Tiny ImageNet, and it's much better to play around with. Some data about the actual input output. So Tiny ImageNet is a subset, like I said, of the bigger data set. It has around 100,000 images in the training part of it and 10,000 in the test set. Each of these images is a small 64 by 64 pixel image. They're colored images, so you have three color layers, R, G, and B. And there are 200 classes of images. It goes from everything like, animals, just everyday products, plants, anything you want to talk about. It makes it a bit tricky to train a model accurately on this because when you have 200 different classes which aren't really related to each other, you need to figure out a model that can generalize very easily. And so that was part of the fun of working with this kind of project. For evaluation, we use the classic, cross entropy loss and accuracy for testing out how good our model does and how it compares to the others. So first off, we built a very simple classic CNN model just to get our hands wet to see how this was going. So we had multiple convolutional layers, each of them halving the image. So we went from 64 by 64 to 32 by 32, 16, 8, 4. And we flattened it out. We had around 8192 neurons that we then put into dense layers to bring it to 200, which was the number of classes that we wanted. Put it out into a loss layer and figured out how good this was. There were dropout layers of 0.5 after each convolutional and dense layer, and all of our activations were leaky ReLU. There was a final batch normalization and a softmax at the end just to bring everything into that 0 to 1 weight to figure out which of the classes it was meant to be. It was very basic, a simple CNN, and it didn't really perform the best. We had around 0.8 of training loss after around 50 epochs, but our accuracy was 30%, which I mean is better than the 1 by 200 you would get by choosing something randomly, but we wanted to build upon this and maybe get to around the 70s, 80s just to make this model better. Okay, so we figured a classic CNN might not be the way to go about this because we have so many models, so many classes rather. So let's try splitting the image into different parts. This time what we did is first our 64 by 64 image was too big for the memory that we had. We're not really working with a big memory size here, so we decided to shrink it, make it a 16 by 16 image, split it into different patches. So our images to patches layer takes that 16 by 16 image and switch it into 4 by 4 images. Each of them are now analyzed on their own. You put them into a separate dense layer, you flatten them out. You take a cross product of that with itself just to make sure that we know how each of these smaller images and their parts relate to each other. You put that into a dense layer, flatten it out, and then put it into a dense layer again to bring it to our 200 classes. Put a softmax at the end. So this time we don't really want to analyze it in a CNN fashion. We're trying to build a little hacky version of an attention model here, where you take the image and you take different parts of it and figure out how they relate to each other. So yeah, we had a max pool to make sure that we could manage the size of it. We had different independent layers for each dimension and an outer product just to make sure that we know how they work with each other. It worked much better this time. We had a training accuracy of around 91%, but it really overfit on that training set. Like our testing accuracy at the end of this was just 5%, which is very, very poor. And we think that this happened because we just had a single large dense layer and nearly all of the training just happened there. We didn't split it up into different layers. One way that we decided to really tackle this was, okay, let's maybe add more layers there and see how that works out. Around this time, we were like doing more research and we found this thing called a vision transformer and transfer learning really. And so we figured, okay, we've already made a kind of attention model here. Instead of us trying to build it on our own, not really working out the way we wanted, let's take something that was already built, something similar to this, and see how we can modify and edit that to work for us. So we found a pre-trained vision training model, which was built for over 1,000 classes. We decided to, since obviously we don't have those many, we had to modify the head of it to bring it down to 200 classes. We froze the other layers because we don't want to touch those, we don't want to edit those. So out of the potential 86 million parameters that could have been trained, we now are left with around 150k of those. And so a vision training model, a vision transformer, is pretty similar to an LLM transformer in that sense. We have encoders because we're taking the images, we're generating patches of images and analyzing those. There's no real decoder because it's not like we're spitting out words or anything. We just need to classify these into one of those 200 classes. There aren't any convolution layers whatsoever. We're not paring down the image in any way. We're just taking it into separate parts. And all in all, this is how the structure of it looked. So out of this, each of these, so this model, it takes a very long time to train. Each epoch took around 10 minutes to train. So we decided, okay, well, let's just run this for around 9 epochs, 90 minutes. We started with a loss of around 3.4, and by the end of it, it came to around 0.95, which is pretty good. And our results were also very, very positive. So we had a training accuracy of around 77% and a testing accuracy of 88%, much, much better from the 5% that we had started with. Um, I guess what we really learned throughout this was, hey, if you have a really large number of classes and you want to organize your images into them, a classic CNN probably isn't going to cut it. You're going to have to use some sort of transfer learning. You're going to have to use some sort of way to analyze the images in their whole, as well as parts of them individually. None of us had really worked on transfer learning before, so this was a completely new experience to us. We had to learn about it for the first time and really work on it. We had worked with CNNs to a smaller degree, but nothing on this scale, maybe like 5 classes, 10 classes, nothing on 200 level scale. So it was a pretty good learning experience for us overall. So references, so this is a data set. It's available publicly on a Hugging Face, so anybody can go and access that. There are certain benchmarks that people had already done work on this before, and so we used those. And this is a paper where we really learned about the vision training model, vision transformer, and just how to deal with it. That's it. Thank you.